Right now, at this exact moment, there are two machines in interstellar space. Not one, two. Most people know about Voyager 1, the farthest human-made object ever built. The spacecraft that crossed into interstellar space in 2012 and has been sending back data from beyond the edge of our solar system ever since. The one with the golden record, the one that keeps making headlines, the one that everyone talks about. But there is a second spacecraft out there. Quieter, less celebrated, less talked about. Moving through the darkness 13 billion miles from Earth in a completely different direction, sampling a completely different region of interstellar space, carrying something that Voyager 1 lost before it even reached the helipause. Something that turned out to be the single most important instrument for understanding what lies at the edge of our solar system. It is called Voyager 2, and what it found when it crossed into interstellar space, what its unique, one-of-a-kind instrument measured as it passed through the boundary that no model had ever correctly predicted, did not just confirm what Voyager 1 discovered. It contradicted it. It complicated it. It raised questions that Voyager 1, for all its extraordinary achievements, simply could not answer. Because Voyager 1 was blind to the most important thing at the helipause, and Voyager 2 was not. And right now, in the summer of 2026, Voyager 2 is about to become the most important spacecraft in the history of this mission. Not because of what it found, because of what NASA is about to do to it. A procedure so risky, so unprecedented, so all or nothing in its design that the engineering team nicknamed it the Big Bang. A simultaneous, coordinated reconfiguration of every remaining power system on the spacecraft, attempted across a communication delay of more than 16 hours each way with no backup plan and no second attempt if something goes wrong. If it works, Voyager 2 gets more time, and everything Voyager 1 will attempt in July. Depends on whether Voyager 2 survives, what happens first. Stay with me because this is the story most people have never heard, and it matters more than anything currently being discussed in the Voyager mission. Voyager 2 launched on August 20th, 1977, 16 days before Voyager 1. Despite having a higher number in its name, the naming is not a mistake, and it is not a clerical error. It reflects the order in which the missions were expected to reach their targets. Voyager 1 was on the faster track, aimed at a trajectory that would take it past Jupiter and Saturn before angling out of the solar system entirely. Voyager 2 was given a longer, more complex route, one that would allow it to do something Voyager 1 could not. Something that at the time of launch no other spacecraft had ever done, and that nearly 50 years later still no other spacecraft has repeated. Voyager 2 is the only spacecraft in human history to have visited all four of the outer planets. All four. Jupiter, Saturn, Uranus, Neptune, every single one of the gas and ice giants in our solar system. Seen up close in detail with instruments designed to read their atmospheres and magnetic fields and moon systems, Voyager 1 visited Jupiter and Saturn and then departed northward out of the ecliptic plane, sacrificing the possibility of reaching Uranus and Neptune in exchange for a closer pass by Saturn's moon Titan and a faster path toward interstellar space. It was a deliberate choice. Two spacecraft, two missions, two different answers to the question of what the solar system's outer reaches actually look like. The price Voyager 2 paid for visiting all four planets was time. Its trajectory, shaped by the gravitational assistance of each planet in sequence, took longer. Voyager 1 crossed the helipause in August 2012. Voyager 2 did not cross it until November 5th, 2018, 6 years and 3 months later. 6 years during which Voyager 1 was already in interstellar space, already measuring the plasma and magnetic fields beyond the boundary, already sending back the data that was confounding scientists and forcing them to reconsider their models. For 6 years, the data from Voyager 1 told scientists something extraordinary was happening at the helipause. But the story was incomplete because the instrument that would have let Voyager 1 tell the full story had stopped working in 1980. Here's the thing about Voyager 1 that almost nobody mentions when they talk about what it discovered at the helipause. Voyager 1's plasma science instrument, the device designed to directly measure the temperature, density, and flow velocity of the plasma both inside the heliosphere and in the interstellar medium beyond, stopped functioning in 1980, not at the helipause, not in interstellar space, before it even reached Jupiter's orbit on the outbound leg of its journey. 4 decades before it crossed the helipause, before any of the interstellar science happened, the instrument that would have been most useful for understanding what the helipause actually looks like from the inside had already failed. This meant that when Voyager 1 crossed the helipause in 2012, it did so without the ability to directly measure the plasma on either side of the boundary. Scientists could infer what was happening from other instruments, from the cosmic ray detector, from the magnetometer, from the plasma wave subsystem, but they could not measure the plasma directly. They were working around a gap that had existed for 32 years by the time the crossing happened, and they could not fill it. Voyager 2's plasma science instrument was still working. When Voyager 2 crossed the helipause on November 5, 2018, it was carrying a functioning plasma sensor that Voyager 1 had lost before the Cold War ended. And that instrument at that boundary produced a data set that researchers described as historic. The first direct measurement of the plasma on both sides of the helipause inside the heliosphere and in interstellar space, taken simultaneously as the spacecraft actually crossed the boundary for the first time in history. 5 papers published simultaneously in Nature Astronomy in November 2019 described what Voyager 2's instruments found at the helipause. And what they found contradicted the models in ways that were genuinely shocking to a field that had been working with Voyager 1's incomplete data for 6 years. The first surprise was the thickness of the boundary. Scientists expected the helipause to be a relatively thin, sharp transition, a defined line where the solar wind ended and interstellar space began. Models had placed this boundary as a narrow zone, maybe a few 100,000 kilometers wide, where the hot, fast solar wind met the cold, dense interstellar plasma, and the two environments blended before separating. What Voyager 2 found was a layer, a distinct transition zone, roughly 100 million miles wide, sitting just outside the helipause, not on the inside where the solar wind lives, on the outside in what was supposed to be interstellar space, where interstellar plasma was supposed to begin immediately. Instead, Voyager 2 detected a region of interstellar particles that had pushed inward through the helop like roots pushing through rock. Tendrils of interstellar material extending more than 100 million miles inward from the boundary, mixing with the solar environment in ways the models did not predict. Voyager 1 had seen something similar before it crossed the helipause, but different. Before crossing, Voyager 1 entered a region where the outbound solar wind had slowed almost to a stop, a stagnant zone just inside the boundary, where the wind essentially ran out of momentum before it could push further outward. Voyager 2, approaching from a different direction and crossing the helipause at a different point, saw something completely different on its approach. A thin layer that was nearly the same width as Voyager 1's stagnant zone, but had different plasma characteristics entirely. 2 spacecraft, 2 crossings, 6 years apart, different parts of the helipause, completely different boundary structures. Stadiosis, principal investigator for the Low-Energy Charged Particle Instrument at the Johns Hopkins Applied Physics Laboratory, described what this meant with a clarity that captured the scientific community's reaction perfectly. The fact that both probes encountered the helipause at almost exactly the same distance from the Sun, 121.66. Astronomical units for Voyager 1 and 119 astronomical units for Voyager 2, was itself deeply surprising. One crossing happened near solar maximum when the Sun's output was high. The other happened near solar minimum when activity was low. The size of the heliosphere was expected to change significantly with the solar cycle expanding during periods of high activity and contracting during quiet periods. Instead, both probes found the boundary at essentially the same distance. "We don't understand why that is," Krimigas said directly. "We do not understand why." From one of the senior scientists on the Voyager mission with decades of data from these spacecraft, that statement is not a casual admission. It is a declaration that something fundamental about the relationship between the Sun's activity and the size of the heliosphere does not work the way the models say it should. The second major surprise from Voyager 2's helipause crossing was about temperature. The plasma inside the heliosphere, carried outward from the Sun by the solar wind, is hot. Not hot in the sense of everyday experience. The solar wind plasma is hot in the sense that its particles are moving extremely fast, which is how temperature is defined in plasma physics. Scientists expected that as this hot plasma reached the helipause and encountered the colder, denser interstellar medium pressing in from outside, the transition in temperature would be one of the defining characteristics of the crossing. What Voyager 2's plasma instrument measured was something different. The temperature drop, the helipause, was sharp, much sharper than models predicted. The plasma went from the hot solar wind environment to the significantly colder interstellar medium in a zone narrower than expected. But what made this finding particularly striking was what happened to the density inside the heliosphere. The solar wind plasma is relatively thin. Outside the helipause in interstellar space, the plasma is significantly denser. Both Voyager 1 and Voyager 2 confirm this, adding the 2 data points together to give scientists their first stereo measurement of interstellar plasma density. The space between stars is not empty. It is filled with plasma more than 40 times denser than the solar wind at the helipause. But something else came from Voyager 2's plasma measurement that changed a specific and important part of the picture. The temperature of the interstellar plasma, directly measured for the first time by Voyager 2's functioning plasma instrument, was 30,000 to 50,000 degrees Kelvin, hot by most everyday standards, but far cooler than the plasma just inside the helipause boundary, which the spacecraft's instruments had measured at tens of millions of degrees. The boundary was real, the temperature contrast was real, and the direct measurement of the interstellar plasma's temperature, impossible for Voyager 1, hiding a response to make without a functioning plasma instrument, gave scientists a baseline number they had previously only been able to estimate from theory. The estimate had been off by a factor of 2. The third surprise, and the one that Ed Stone, the Voyager project scientist at Caltech, who had held that position since before either spacecraft launched, called most remarkable, was about the helipause itself. It leaks, not metaphorically, literally. The boundary between the solar wind and interstellar space is not a clean wall. Particles cross it in both directions. Voyager 1, on its approach, had detected what appeared to be tendrils of interstellar particles punching inward through the boundary, entering the heliosphere from outside. Voyager 2, on its approach from the south, saw something different. A trickle of low-energy particles extending outward from the helipause leaking into interstellar space before the spacecraft had even crossed the boundary. The leakage was confirmed from 2 different entry points at different times during the solar cycle in different parts of the helipause. Whatever was causing it was not a local phenomenon. It was a property of the boundary itself. Something fundamental about how the helipause works that was absent from every model built before the Voyager crossings. 2 spacecraft approaching from different directions, 6 years apart, both finding the same leaky boundary. Different mechanisms on different sides, interstellar particles pushing in from one direction, solar particles leaking out from another, but the same underlying conclusion. The helipause is a border that materials cross regularly in both directions. It is more like a coastline than a wall with surf running in both directions at the interface between 2 oceans. The Voyager probes are showing us how our sun interacts with the stuff that fills most of the space between stars and the Milky Way galaxy. Stone said in the announcement accompanying the 5 Nature Astronomy papers, "The choice of words is careful and significant. Not how the sun ends and interstellar space begins, how the sun interacts with interstellar space. Not a clean separation, but a continuous, messy, dynamic relationship between 2 environments that do not stay neatly on their own sides of the boundary. And both spacecraft are still in a perturbed transitional region. Not yet. In undisturbed interstellar space, even at 13 and 16 billion miles from the sun, both Voyager probes are sampling an environment that is still being influenced by the solar system they left behind." Now, step back from the science for a moment and think about what Voyager 2 actually represents in the context of the entire Voyager mission, because the discovery story is only part of it. When Voyager 2 was given its trajectory, not the one that took it past all 4 outer planets before heading for interstellar space, that decision was made knowing that it would arrive later, knowing that it would cross the helipause in a different direction from Voyager 1, knowing that the 2 spacecraft would provide different views of the same boundary. This was not accidental. The Voyager mission planners, working in the 1970s with computers less powerful than a modern pocket calculator, designed a 2 spacecraft mission specifically to avoid the limitation of a single data point. One spacecraft cannot tell you whether what it found is typical or unusual. 2 spacecraft approaching from different directions at different times can begin to build a picture of the whole. What they could not have fully anticipated was that the instrument that turned out to be most critical for understanding the helipause crossing, the plasma science instrument, would fail on one spacecraft and survive on the other. That Voyager 2's plasma detector, still functioning after more than 4 decades of operation in the radiation environment of the outer solar system, would provide the data that Voyager 1 simply could not give, filling a gap that had existed in the Voyager dataset since 1980. The division of labor between the 2 spacecraft was planned. The specific way that division played out was not. That is the kind of science that Voyager 2 represents, a planned contribution that exceeded its design in ways nobody fully anticipated. A mission that was supposed to end in 1981 and is still transmitting data in 2026 from a region of space that has never been directly sampled before, with instruments that have outlasted every prediction made about their operational lifetime. Right now, in the summer of 2026, the focus of the Voyager mission engineering team at JPL is on Voyager 2 inches away it has rarely been before. Voyager 2 currently has 3 operating science instruments. The plasma science instrument, the one that made the helipause crossing measurements possible, is among them. The magnetometer is operational. The plasma wave subsystem is operational. These 3 instruments working together are providing something no other asset in the history of astronomy has ever provided. A continuous real-time in-situ measurement of conditions in the interstellar medium, taken from a spacecraft physically located in that medium and moving through it at 34,000 miles per hour. But the power budget is shrinking. the same process that is slowly consuming Voyager 1's operational capability. The steady, mathematically certain decline of plutonium-238 as it decays at a rate that removes 4 watts from the spacecraft's available power every year is doing the same thing to Voyager 2. At launch, each spacecraft had approximately 470 watts from its 3 radioisotope thermoelectric generators. Today, Voyager 2 has slightly more power remaining than Voyager 1, which is why it has 3 operating instruments, where Voyager 1 now has only 2 after the LEC shut down in April 2026. But that margin is not large, and it is shrinking by 4 watts every year. The Big Bang is meant to change that. The procedure, as described by NASA's Jet Propulsion Laboratory, involves swapping out a group of powered devices all at once, turning some things off, and replacing them with lower power alternatives to keep the spacecraft warm enough to continue gathering science data. The name comes from the all-at-once nature of the reconfiguration. Not one change at a time, tested and verified before the next change is made. Everything simultaneously. A complete restructuring of how power flows through every remaining active system attempted in a single coordinated operation across a communication link, where each command takes more than 16 hours to arrive and each response takes more than 16 hours to return. The reason for doing it all at once rather than incrementally is specifically about the risk of intermediate states. During any power system reconfiguration, there are transitional moments where the system is neither in its old configuration nor in its new one. Those transitional moments can trigger fault protection systems, automated safety mechanisms built into both spacecraft that will begin shutting down components on their own if they detect the power draw exceeding what the generators can supply. The whole point of the Big Bang is to minimize the time spent in those dangerous intermediate states by making all the changes simultaneously, skipping through the transition as quickly as possible. If it works, if the new power distribution configuration reduces waste across the system enough to recover meaningful headroom in the power budget, it could extend the operational life of Voyager 2's science instruments by at least a year, possibly more. And if the Big Bang succeeds on Voyager 2, the same procedure will be attempted on Voyager 1 no earlier than July 2026, with the hope that a successful outcome there might even allow the reactivation of the LEC instrument shutdown in April. Voyager 2 goes first, not because it is less important, but because it is slightly closer, slightly better powered, and therefore the safer test subject for a procedure that has never been attempted before. What is at stake in keeping Voyager 2's instruments alive as long as possible is not a question with a simple answer. It is several questions layered on top of each other, each one pointing to a gap in human knowledge that only these 2 spacecraft are currently capable of filling. The structure of the heliosphere is one of those questions. The 5 Nature Astronomy papers from 2019 established that the helipause is leaky, that it is at approximately the same distance from the Sun regardless of solar activity, that the interstellar plasma on the other side is denser and cooler than expected, and that the boundary structure looks different depending on which direction you approach from and what instruments you carry. But those findings raised as many questions as they answered. Why is the helipause at the same distance during solar maximum and solar minimum? What determines where the boundary sits, if not the strength of the solar wind? What is causing the leakage of particles in both directions? And how does that leakage vary over time as the Sun moves through different regions of the galaxy's interstellar medium? The shape of the heliosphere itself remains genuinely uncertain. Some models predict that it has a long, comet-like tail stretching away from the Sun in the direction opposite to its motion through the galaxy. Others suggest it is more spherical or even lemon-shaped. Voyager 1 and Voyager 2 are sampling 2 points in the heliosphere's outer structure, one in the general direction of the nose, one toward the flank, and their combined data is one of the primary tools scientists have for testing these competing models. The longer both spacecraft remain operational, the more data accumulates, and the better constrained the models become. The interstellar magnetic field is another open question. Both spacecraft have measured the magnetic field in interstellar space beyond the helipause, and the direction of that field has implications for how the heliosphere is oriented relative to the galaxy's large-scale magnetic structure. Voyager 2's magnetometer, still functioning in 2026, continues to contribute measurements that help map the local interstellar magnetic field in the southern hemisphere of the heliosphere, a region that is different from where Voyager 1 is sampling in the north. And beneath all of these specific scientific questions is the broader issue of what happens when both spacecraft eventually go silent. There is no replacement. There is no follow-on mission in interstellar space. There is no instrument within 50 billion miles of where these 2 spacecraft currently are. There will not be for decades. When the last of their instruments goes dark, the map they have been drawing of the interstellar medium will stop being updated. And every question they raised but did not fully answer will sit unanswered, until some future mission, one not yet funded, not yet designed, not yet approved, eventually makes the same journey and arrives at the same boundary. Voyager 2's achievements, listed plainly, are almost too numerous to fully absorb. It is the only spacecraft to have visited Uranus. During its January 1986 flyby, it discovered 10 previously unknown moons and 2 new rings around the planet. It measured the extreme axial tilt 97.77 degrees of Uranus and its interior composition as an ice giant, and found a magnetic field so offset from the planet's rotation axis that it still challenges models of how planetary magnetic fields form. It is the only spacecraft to have visited Neptune. During its August 1989 flyby, the last planetary encounter of the Voyager program, it discovered 6 new moons, including Proteus, which turned out to be large enough that it probably should have been found from Earth before Voyager arrived. It measured Neptune's supersonic winds reaching 2,400 kilometers, h, the fastest measured in the solar system at that time. And it made detailed observations of Triton, Neptune's largest moon, finding active nitrogen geysers, shooting material 8 kilometers into the thin atmosphere, and determining that Triton was almost certainly a captured Kuiper Belt object, a world that formed elsewhere and was pulled into Neptune's orbit by gravity, its surface shaped by the tidal heating that results from an orbit that has been slowly circularizing ever since. It discovered a 14th moon at Jupiter during its 1979 flyby. It provided data on Saturn's rings that revealed a complexity of structure previously invisible to Earth-based telescopes. It confirmed the active volcanic eruptions on Io that Voyager 1 had first detected, watching Prometheus erupting in a 200 kilometers high plume of sulfur dioxide frost. And it returned the images of Europa's icy surface, the fracture patterns, the lack of large craters, the reddish-brown material staining the cracks between ice blocks that first suggested the possibility of a liquid water ocean beneath the ice. Images that seeded decades of scientific interest in Europa as a potential habitat for life and eventually led to the Europa Clipper mission currently in operation. All of this from a spacecraft launched August 20th, 1977, 49 years ago. Built with technology from an era before the internet, before personal computers, before GPS, before cell phones, designed to last 4 years. Still transmitting, still gathering data, still providing because of the unique route it was given, and the instrument that survived where Voyager once failed. Something that no other spacecraft in history has provided. Direct measurements from inside interstellar space from a different direction than Voyager 1, with a functioning plasma instrument for the first time in history.